representation that are not as easily... Thank you. I'm going to tell you a story about the most fascinating organ, as far as I'm concerned, in the human body, and that is your brain. And this story is going to build on Lisa's talk because I use some of these methods that she was talking about, these pattern algorithms. And this story is based on the work of my wonderful German PhD student, Lena Teichmann. I'm going to apply these particular methods that I'm going to tell you about, to a really important question of how we represent colour. So colour is crucially important in our world. It tells us what to eat, what to drink, what not to drink. And probably most of us will agree that this luscious-looking tomato is what we would call red. And perhaps even that when you look at this strawberry, you can tell that actually if that was real, that would also be red. But when we get to this dress over here, that agreement is likely to break down. Some of you are going to see that as blue and black, while others are going to see it as white and gold. That disagreement comes from the fact that your perception of colour is not really just due to what comes in, but it's due to what's in here already. And so that integration of information is what gives you your perception of colour. In the case of the dress, the illumination is ambiguous, and your brain automatically corrects for perceived illumination, resulting in different experiences. So these experiences I just told you rely on what's already in here. How are we going to study that? Well, I'm going to tell you about a technique that measures the tiny magnetic fields generated by your brain cells when they talk to each other. So they use an electrical communication, and every electrical communication elicits a tiny little magnetic field, and if enough of those are doing the same thing, then we can measure it with a spiffy device that has very, very sensitive sensors. So using MEG, we looked at colour representation in the brain by showing participants loads of stimuli that are red and loads of stimuli that are green, and looking at the neural pattern, so the pattern of brain activity across these senses when people are seeing red things versus green things. We feed that neural data into a computer algorithm, so beautifully set up, and we look at analysing the pattern. So we teach that computer, oh, this is brain data from the participant seeing a red thing, this is brain data from a green thing, and I'll show them lots of examples. And then we give it a new set of neural data from that participant and say, was that participant seeing a red thing or a green thing? If there's information in that magnetic signal, then we should be able to distinguish better than chance whether it was a red thing or a green thing. And indeed, that's what we can do. So this is the point at 90 milliseconds where your brain activity for red and green can be distinguished. Now we have this technique for actually looking at what the brain might be representing about colour. We can use it to ask some important questions about other aspects of colour representation that are not as easily accessible. So once again, in this study, we train on red things versus green things, and then we test now on neural data from participants seeing things that are usually red versus things that are usually green. Now, if the way you represent colour when you perceive it, and the way you represent colour knowledge share something in the way that your brain represents it, then we should be able to train on real colour and test on implied colour. And that's indeed what we can do. So what you see is that it happens a bit later, it takes 150 milliseconds, but the similarity is there. Now, some people have called this sort of decoding approach mind reading. I wouldn't go that far. But it's important in this case because it gives a proof of a method that we can study brain representations for things that can't be directly observed. So we're applying this to a phenomenon called synesthesia, colour experiences from non-coloured stimuli. My colleagues are applying it to test for language comprehension in children that can't tell you that they can understand you, and even potential for vegetative states. Thank you.